If I applied for the grad course next semester, would you like consider studying?
Yeah,
As undergrad.
a waiver. Yeah,
Yeah.
I think that would be okay.
I hope today is like a substantial increase in difficulty, so people will drop it.
So, where are you on the list? Where are you on the list?
There's no list anymore.
Ah,
It's for free for all.
wait, so there's no waiting list anymore?
There's no waiting list, and it's just a section full, and whoever gets there first
I see.
can.
Good luck. Okay, hi everyone. Hello, welcome. Okay, so welcome to the first tutorial where we're going to be doing exercises. These exercises are going to reflect the kind of stuff that you might see in an exam situation. So it's a nice idea to practice that here. We have 5 different exercises for today, and we're going to start kind of with a warm-up. We'll take less time for the first few, and then like the last 2 will involve some more thinking. And we'll kind of try to kind of push on the frontiers of what we've learned last time. Okay, so the way that I'd like to do this is I will present an exercise one at a time on the board. I will give you a few, I'll give you some minutes for it. I mean, I think that it would be great if you all begin by thinking about the question alone for like, 1 or 2 minutes. Then you can start talking to your neighbor and see if you have the same answer. You can discuss. Okay, so, it should be kind of collaborative. While you're doing this, I will, feel free to raise your hand. I'll come by, I'll clarify anything about the exercises, answer any questions. Okay, is that good with everybody? Okay, so let's start. Oh yeah, and if you don't already have a group, it's a good idea to form groups. So feel free to do that via Piazza or by talking to your classmates in person. Here's the first question. So consider a table that, as we saw last Wednesday, can be allocated as a linked list of pages. And suppose we're trying to scan this page, scan this table. Okay, so simple question. What kind of throughput in terms of, say, megabytes per second would you expect if you're doing this on an SSD versus a disk? So this is a question that requires you to know something about, right? Like, we talked about the kind of IO patterns you'll get if you're trying to traverse a linked list. We talked about like the kind of bandwidth characteristics we should get with random versus sequential writes if you have a disk or if you have an SSD. So let's see if you can figure this out. So can somebody remind me something about I know. Keep thinking for a second. I'm expecting that from. Okay, so first of all, are we doing random or sequential access here? Okay, we're doing random access, we all agree. Who can remind me what is the cost of, say, a random page read with a disk drive? Hmm? Yeah, 15 milliseconds, but I would only expect you to remember the kind of order of magnitude, right? So, for my part, just remember 10 milliseconds, that's enough. Who can remind me what is the approximate random read cost for an SSD? Huh? Yeah. Micro. Okay, so an SSD random read will take you about 100 microseconds. Okay, so I'm telling you because these are important numbers to know, right? If you're building a system, it's important to know which orders of magnitude you're dealing with. So, your CPU takes nanoseconds to, do computations. An SSD read is orders of magnitude more expensive, and yet only like 100 microseconds. Right? And a disk read is something like 10 milliseconds, right? So orders of magnitude more expensive than that. Okay, so based on these numbers, you can reason about it. Does somebody have a quick figure they'd like to give me based on this? Okay, let me give you the answer because this is just kind of a warm-up, and I'm just going to give you kind of what I expect, right? So you don't need to know that much to answer this kind of question, right? So, this IO takes about 10 microseconds, and like we're reading things at the granularity of pages, so 4 kilobytes at a time. Right? So you might expect 0.4 megabytes per second. Right? An SSD is 2 orders of magnitude more fast with respect to random reads. So you might expect 40 megabytes per second, right? So, not rocket science yet. Okay, and then, we also saw how to improve throughput for this kind of structure. So what are the 2 techniques that we looked at to improve throughput for structuring a table? A directory. And why is that good?
Because we can then, on an SSD, we can then start reading things synchronously.
Asynchronously.
Right.
Yes. Okay, that was one technique. Good. Second technique. Yeah.
Pages?
Huh?
Larger pages?
So not really larger pages, but clustering pages as extents, right? Storing them contiguously because that's going to be good for our, disk sequential reads. Okay, so this is kind of a typical question, like for an exam situation. I'm asking you to, understand the core concepts, maybe crunch some numbers. Okay. Let's move on to the next one. We're still sort of in warm-up phase. This will get a bit more interesting. Okay. Consider a database that's subject to uniformly random reads. So what I mean by this is that every data entry in the database is equally likely to be accessed by the next read. We learned about various different buffer management and eviction policies in the last lecture. What is the best one for this kind of workload? Don't tell me just yet. And then, like, how would your answer change if it's not a random workload, but a skewed workload? So yeah, some of you might already know the answer, but keep it for yourself. Let's think about it for 2 minutes. Discuss with your neighbor, maybe. Okay, so I think you're quieting down. I think probably some of you have reached conclusions. So who has an answer? All the hands that want to have an answer. I feel like most of you should. Okay, let's go here. So random eviction would indeed be the best policy for this, despite everything that I told you on Tuesday, right? On Tuesday, I said I really argued strongly against random eviction. However, if you have a uniformly distributed workload, that is going to be the best policy. And it's going to be the best policy, actually, before I show you the reasons. Why is it going to be the best policy?
Because everything is uniformly used. So we don't really care about like which ones we should store in memory because it's all going to be random, right? So why waste any storage?
Okay, so you're implying that we're gonna use less space for the buffer pool if we use random?
We're going to have more space to store like actual stuff like this.
Okay, so we're gonna save some metadata. What other advantages do we have?
Speed.
So,
Random eviction is the best CPU performance.
okay, perfect. Yeah, that's good. So we're gonna save CPU overheads. Anything else? Okay, so the other thing is keep in mind that with random eviction, we can actually use 100% of all the frames in the buffer pool. Otherwise, we need to keep some free space to allow the hash collision resolution strategy to have effect. And usually, right, you need at least 10 to 15% of your hash table to be empty to actually support fast operations. Okay, so these are the reasons. Okay. So what about if my workload is heavily skewed? And by heavily skewed, I mean that some pages are accessed more frequently than others. How would your answer change? Yep. Yep, exactly. So yeah. So in the typical case where you actually do have a skewed workload, and most workloads in the world are skewed, you want to use clock or LRU. Okay. Everyone happy? Cool. Okay, here things get a bit more interesting. So the way we've learned things on Tuesday is we said that our storage is divided into pages. Each page stores a bunch of entries. And I love these pages, and my unit of caching things in memory is one page at a time. Now you can imagine that another way of doing this would be to actually store things at the granularity of individual entries in the buffer pool, as opposed to at the granularity of pages. Does that make sense to everybody? So what are the pros and cons here? So I could map thing. Okay. Any questions? Does that make sense? Yes?
Are we considering that to increase our fixed size or variable
Sorry, say that again?
Are there entries fixed size or variable size?
The entries?
Yeah.
Let's assume for this question they're fixed size. I don't think that assumption actually really matters for the question, but for simplicity, we can assume that. Does anybody have a question about the question, about what the question is asking?
One of them is getting there. Then you have to do it right at the beginning. You have to bring in the application. You write it. That's one thing that you have to write. Yeah. So, in terms of programs, obviously, we can much more efficiently if we actually speak to them. Because you don't sort of hire them, if you don't try. And I don't have to talk. You don't sort that wrong. Much more based on space. About creating that lots, it's what's the law in terms of.
So how about you? Okay, it looks like a bunch of you have answers, so let's bring the discussion back here. Okay, so what's the main pro of doing this? Why would we want to do this in the first place? Yep,
Less space in the buffer pool so that more entries will cover.
okay, that's good. You can make that a little bit more crisp. So somebody want to make that, elaborate on that a little bit, even though that was exactly the right intuition over there?
If you only need one specific entry in a page, like you're not wasting caching the rest of the page when you're only like.
Yeah.
that one entry is fine.
Yeah, that's right. So you might have a situation where, right? So suppose you have, we have multiple entries in a page, and only a few of them might be hot, or only one might be hot, right? So the caching of the page granularity forces us to store a lot more data than what is actually hot potentially. So if we only stored the hot entries in the buffer pool, we could save a lot of space, and that could allow us to store a lot more hot stuff in memory, right? Okay. Questions? Feelings? Okay, good. What are the cons of doing this, and why do we not actually really do this in practice? So over there at the end.
Say something from dirty and write it back in. We have to read the entire page to find which entry was like exactly changed when we have to.
Yep,
Right.
exactly right. And why is that not the case when we cache things at the block and at the page granularity?
Because you already have the entire page, just write it in.
So write it back. Yeah, exactly.
Reading the writing.
Exactly. Excellent. So that's con number one. There are a few more cons. What are some other cons? So over here.
Would it take more, there'd be like more CPU overhead because there's a lot more.
Yeah, conceivably there will be higher. CPU is a good question. So what's your argument for why there would be a higher CPU overhead? Yeah, at the same time, the overheads of the buffer pool are still constant, so it's not totally clear to me if number of entries would affect it, but there are other cons, yes?
I think what you said, you probably need a really big table. Store everything,
Mhm.
store all the entries.
Mhm.
The memory overhead would be a lot more.
Okay, so you're talking about memory overhead, and memory overhead because of what?
The table, which is storing everything by rather than by page.
Okay,
So there's input output overhead in the sense that you have to, like, if you need to read like a table, you need to. Each entry you have to have like one read and then. you
Yes.
Need to write, then you
that's correct.
like too many writes, one by one.
Mhm. Good, over there?
Yeah, sort of the same thing. So you want to read a bunch of entries for one page. With normal system, you can just read the page and then you have a page in your buffer. But with this system, say you have like 100 entries in the page, you have to do 100 operators to get everything.
Yeah, okay, so you're kind of saying, and I think you said the same thing over here, right? So basically, I think you both said that if you're trying to actually read all page, oh, if you're trying to actually scan, you might actually have to do many random accesses in your buffer pool as opposed to kind of having the pages clustered. That's a great point. Okay, so I think we kind of I think we covered all of the points so far. So the first one, as one of your colleagues said, if you evict an entry from the buffer pool here, you have to read a whole page. You have to first of all find the page that the entry belongs to, read it to memory, and then write it back. So you have to do an extra read IO. It's not great. Reads are expensive. IOs are expensive in general. The second problem is there's going to be heavier metadata because here we're going to be applying the metadata at the granularity of entries versus at the granularity of pages, right? So it's like the same amount of metadata, but it's applying for the same amount of metadata per cacheable entry, but the entries are much smaller, right? So the relative overhead of metadata is much higher. That's what the second point says. And the third point says, this is not so good if we're actually trying to scan the data. This is very good if we have selective queries. Selective queries are queries that only try to read very few data items. But if we have scans that try to read a substantial amount of the data in a table, this is pretty bad because it's going to force us to do a lot of random accesses across our hash table in memory. And does that make sense to everybody? Questions? Yes.
On a storage batch level or something on the file, so reading then
This is at a storage. This refers to a storage level, right? And it refers to so. Yeah.
then it doesn't really have to flush as soon as you right? And even if it's like that. Right.
Okay, so you could apply techniques like batching. But batching might work. I mean, right? So like, for instance, if you have multiple entries that are all dirty, they've been updated, and all of them belong to the same page, then you can benefit from, reading the page, putting all the entries that have been updated on that page and flushing that back, right? But how effective that's going to be will actually depend on your workload. So it's hard to guarantee that that's going to be effective. And secondly, you'll probably require some extra bookkeeping and extra computational work to understand in the first place that multiple entries belong to the same page. So that mapping is going to be non-trivial to implement. Okay. All right. I think we can move to the next one. Okay, so. Okay. Everyone happy? Okay, I hope so. Otherwise, come to me and talk to me at the end of class. So recall one of the methods we saw on Wednesday for how to make efficient insertions into a table. We talked about how we can just buffer new insertions in memory and then flush that buffer as, a page when it fills up. And this allows us to, achieve, right, a much better IO cost because we flush a few new entries for each IO that we do, as opposed to, right, having to read a page, write something on it, and write it back. Okay. So I hope you all remember this. Now consider the following situation. We have a workload that only consists of insertions and deletes. So the deletes, as we said, they find the entry, you find the entry that you're trying to delete, and you create a hole in the table. For now, let's assume we're using fixed size entries. And let's also assume that whenever there are X holes in the table, we compact the table. So we're gonna reread and rewrite the whole table, but contiguously to avoid wasting space. Make sense? Okay. For simplicity, let's assume that in order to find the page that we want to delete, we have an oracle that tells us exactly where the page we want to delete is. So we don't actually need to scan the table to find the entry we want to delete. This is an unrealistic assumption, but let's just assume that we can do this for the sake of the question. Okay. So, okay. So then the question is, analyze the worst case amortized cost of insertions and deletes in terms of IO in the disk access model. Any questions about the question? I'm not sure I understand the question. So, like, the number of valid entries. I think the worst. Multiple entries. I mean, entries on pages. It's small or about zero. You know what, to simplify the question as well, let's also kind of assume that like the table kind of stays in the same size, right? So insertions might happen, then some deletes might happen, but the table is not significantly growing or significantly shrinking with time. Just assume that it kind of stays same size.
Yeah, so.
Okay, let's start because the question after this one is more fun and I want to get to that. Okay, so first of all, okay, your attention back here. What's going to be my cost of insertions? The cost of insertions is not a trick question. Yeah, it's 1 over B. Right, that's exactly what we saw in the lecture. And this is because, as insertions, like you only do the garbage collection as, you have too many holes, but insertions don't affect the number of holes. You can just continue inserting. So it's just 1 over B. Okay, that's the first part of the answer. I think the second part of the answer is, okay, so what's going to be your delete cost? Like without the garbage collection part, without the compacting the table part. Yes? Huh?
With your
With the Oracle, yes. Sorry? Constant time.
Yeah.
Okay, so you're saying big O of one IO, basically.
Yeah.
Yes, that's right. That's right, because we have the Oracle tells us where to go, but when we get to that entry, we still need to read a page and write a page to delete that entry. So constant time due to the Oracle, right? If we didn't have the Oracle, it would be N over B, because we have to scan the table to find the entry we're trying to delete. Okay, what about the compacting the table part? Big O of N? Okay, first of all, okay, so there are two issues with that answer. The first issue is that we're trying to count IO, not entries. So we're trying to count the number of pages. And second of all, we're not trying to just quantify the cost of the whole process of compacting the table. We're trying to, take that cost, but then see, what is that cost with respect to an individual delete operation? We're trying to compute amortized costs with respect to an individual delete. Yes?
N by B.
And by N divided by B by dx. Why?
Because N by B gives us the total number of pages, and we reorganize all the pages once there are X number of pages. So it's like N by B, the entire thing divided by X, which gives N divided by B.
Excellent. Yeah. So I put the same thing. I just said N plus X, but that also just kind of simplifies to exactly what you said, right? Because we're assuming that N is bigger than X in this question. Okay. You don't need to take pictures because the slides will be posted.
Oh.
So no worries. Yeah.
Why it's over B as well?
Okay, so it's over B because we're doing this accounting in terms of IOs. The table, the number of pages in the table is 1 over B, right? So every time we compact the table, we have to write N over B pages. Okay, and we have to write N over B pages for every X deletes that we execute. Does that make sense? Okay. If I asked you to account for the cost in terms of entries written, it would be N, but I'm asking, it's just a question of like the units in which you express your answer. Okay, any more questions about this? Okay, so we have 10 minutes left. So let's get to the last question, which I think will be a little bit more fun. Okay, so we learned about LRU and we learned about clock, and we learned that these are especially good if we have some entries that are hot. What happens though? What happens if I have a lot of big sequential reads in my workload? So, and in particular, suppose that I have a given buffer size, and suppose I'm issuing sequential read. Suppose I'm issuing the same sequential read over and over, and that sequential read happens to slightly exceed the size of the buffer. What might happen? Let's give it a few minutes, but I can come and talk to you. Does everybody get the question?
Yeah, you're gonna start getting things. We can't. Tired of it. Another challenge. Yeah, break it down to seven. I think I have to break it down to seven. We read one. Use it. Otherwise, so we can't have it all in there. So we have to take it. It's the only way of it. Yes. Then you can always say, well, the new problem of larger stores. You can't just keep.
Let's say if I petition and I. When you get started. Yeah, now you're going through it as you're using the data, where you're kind of like slipping. Chunking. And now we're going down and has like a long. Can we read you? I mean, I guess it was SSD. Actually, if we're reading it. This is. It must have been everything. Yeah, reading. Everything is going to have a notice. How does it go?
Okay, we have 5 minutes left, so let's bring this together. So what's the terrible thing that could happen? What's the terrible thing that could happen if we have sequential? More hands, all of you have spoken so far. A hand that hasn't spoken. All right, well, a hand that has spoken then.
IO overload would happen, so you just have to, get in new pages again and again.
Yeah, okay, yeah. So does somebody want to elaborate on that? Go ahead.
Yeah, so like imagine, let's say your buffer pool only has 3 entries, but you're reading 4 things. So then you read the first 3, they get loaded into the buffer pool. Then you read the 4th one, you have to boot out the first one. The 4th one goes in, then you read the first one again. Then you have to
Yes.
put out the second one, and you just stuck in the loop of constantly having to boot out all once and read the page.
That is basically correct. You're correct. And this phenomenon is called sequential flooding. Sequential flooding of the buffer pool, in this case, clock. So excellent. So here's an animation to show you what that looks like. suppose we're scanning the following table. So I scanned 1 to 6. This all goes into my buffer pool. Note that I'm simplifying things. This is a hash table, so these pages would actually kind of be jumbled up in a random order in the hash table, right? They wouldn't be stored sequentially. But now I want to read page 7, and I don't have space. So my clock handle is going to begin my traversal. It's not going to find any zeros, so it's not going to evict anything. It's going to go back. It's going to find the first 0 and evict 1 to clear space for 7. But now, now I want to read page 1, but I've just evicted it. So I'm gonna, evict the next page, which is 2. So I'm in this really tragic situation where every time I'm evicting the page that I want to read next. Okay, that's sequential flooding of clock. That's a really annoying and terrible situation. How can we address it? Yeah.
I guess the very nice solution is to have a memory.
To use more memory?
Yeah.
Okay.
You can use some form of batching. I don't know what exactly you're saying, but instead of having this, guidelines a clock edits 1 page and you bring back in 1 page, right? Make that one subject order. So the clock kind of edits multiple pages. Maybe you need some better tracking of some sort. But instead of just getting 1 page at a time, you're getting in like, for example, in the 7th one, right? Instead of just getting in the 7th one, you get 7, 1, and 2.
So you want to evict multiple pages at a time and you want to kind of evict like slightly more random pages?
Not random exactly. I guess that's where you can kind of, maybe track a little bit. Maybe you could, in the sense like, if there was something after 7, like 8, 9, 10, so 7, 8, 9.
Okay.
A little bit easier to make a decision there.
Okay. Good thoughts. Other thoughts? Yeah.
I'm just not sure, but maybe if you know that we need to use them again, we just store them somewhere else. So if we know we need to use the 1, 2, 3 again.
Okay, so you're kind of proposing
then
this might require more metadata. You could maybe do a solution like this.
why do you use the book?
Okay. Yeah.
What if we put bundle clocks based on like multiple buffers? So let's say we've got 1, 2, and 3 at the same time. Maybe just 1. We've got 1 and 2 at the same time to share what I'm offering.
So you kind of want to apply clock at a more coarse granularity. So why would that help you?
Simplified pairs, you evict pairs, which might
Then we might just evict like 2 pages at a time and then read the next 2 pages at a time. So I'm not quite sure if that would help unless I'm missing something. Over there?
How to maybe stash the whole buffer in memory, in this, and then just commit to reading from this, because then it's just 1 IO less. You don't have to make it regions.
You want to stash the buffer in memory, like flush the whole buffer? Okay, also an interesting idea. Okay, so there's actually not a clear solution here. I mean, this is an annoying situation. Here's kind of a straw man solution. This is not a good solution, but like it's kind of a caricature of a solution. But you could apply a most recently used policy, which evicts the page that has been accessed most recently. If you actually did that, think about that a little bit. That will actually be better than least recently used in this case because it would keep what you're trying to read next in the buffer. However, this is not a generically good solution for obvious reasons. We're finishing class, so I'm kind of finishing things quickly. A better solution is, if you have, you could record some metadata actually in the buffer pool about, whether the page you've written was read sequentially or not, right? This could be one bit in your metadata for each frame. All right, so, maybe keep track of whether it's a sequential write or not, maybe evict that with a higher priority. Maybe evict things from the buffer pool immediately if it's a sequential read and it's already been consumed and used, right? So there are different solutions to this problem, but it's a nice thing to be kind of aware of this problem, right? And database systems have to somehow safeguard against something like this happening. Okay, we are done. Thank you very much.